I would like actually to give a demonstration of Coriolis first, because most of us probably are pretty familiar with the centrifugal force. However, with the Coriolis force, we are not that familiar. Are you familiar with Coriolis force? Can you juggle 3 balls? Who can do that? You can. Okay. Yeah.
Sweet.
Now we will show. I demonstrate effect of Coriolis force. What's your name?
Taylor.
Taylor. Okay. Taylor. Now show how good you are. Okay, pretty good. Yeah, that's great. Yeah, because now we will make it a little bit more difficult for him. Yeah, I want now to add the effect of the Coriolis force. What I want you now to do is to stand on that platform. So first, I will hold it. Okay, and try to juggle. Okay, you feel comfortable, right? You can stop, right? Now, I will put him in a reference frame which is a non-inertial, because he learned how to juggle in an inertial reference frame of the classroom. He adjusted actually his motions to the forces which are exerted on the balls right now, which are what forces? Just gravity, yeah, because the balls are flying. They are in a free fall. Right now, I'm going to start juggling now. Oops. And what do I have to do actually to turn on that Coriolis force for him? Start to rotate him. What did the ball do? What did the balls do? Yeah, they were started to fly wrong direction. For him, because from your point of view, you saw that the balls are flying exactly like before, right? Now, so actually, this Coriolis force now completely confused Taylor. He didn't know actually where to put the hand because the Coriolis force was taking it away from him. Now, Taylor, I want you to do one more exercise. Try to throw the ball towards yourself. Yeah, like this.
While you're spinning me?
Yes. Something like this. Yeah, can you practice it first? Yeah. Okay. Now get on the platform. Okay, are you ready? Yeah, I was not spinning you. Now I'm going to spin you. So actually do it when you are facing the class, okay? After one spin.
After one spin?
Yeah, I will make one rotation and then you toss it so that others see what you will do. Okay? So have your head. Actually, maybe 2 spins so that you feel comfortable, okay? After 2 spins. Okay, so this is 1. How did you see it?
I saw it, I don't know, go this way and out of my view.
Okay. Well, I don't know. See what you observe. Yeah, let's try it again. Practice it again. Yeah, so do it the same way as you do now, right?
Okay, now on your shoulder.
That's how it went around me.
Which way?
This way.
Yes. Okay. Thank you, Taylor.
So is he supposed to toss it up?
No, he was supposed to do it exactly and he did it exactly the same way as what he was doing when he was not turning, right? But this time I mean, he observed it really. He observed the ball turning this way. It didn't go straight to him, but it turned that way. I mean, we saw actually that it went that way, right? Because for us, it had a certain velocity in this direction. He was still trying to pull it toward himself, but in our reference frame, we recognize that he had to be confused because he assumed that it is stationary. So he accelerated it toward him, forgot about this component of velocity in an inertial reference frame. So in our reference frame, the ball really went like that. Well, but that because he was spinning, look at that. So he starts that the ball is traveling toward him, but by the time he turns this way, ball is traveling there, right? So he actually saw the ball curve like that. This is the Coriolis force in action, and actually over here there was only Coriolis force. Now Coriolis force on Earth causes hurricanes, yeah, because it's exactly. I mean, hold on. When he was spinning like that, which means that it's exactly like North Hemisphere, like on the North Hemisphere. Yeah, let's take a look at the North Hemisphere. And North Hemisphere is turning like that. Angular velocity is up. And, well, the air mass, which is starting from equator, when it travels toward north, it is traveling toward the axis of the Earth. Do you see it? It gets closer and closer to the Earth. Earth is not exactly like a platform, completely flat, but it is like a dome. However, that air mass gets closer and closer to the pole, I mean to the axis. Well, so exactly like this ball over here, that mass of air, when it has velocity upward, it will experience Coriolis force to the right. So it will turn this way. Well, if it will turn this way, it will produce low pressure here with whatever pressure is. So then it becomes, well, that air around will push that mass of air toward that low pressure region and result in that centrifugal force, which will make it to spin that way. And we get a hurricane. If you look at the other side, the southern side of the Earth, the hurricanes will have to spin the other direction, also because of the Coriolis force. All right, now I wanted to actually solve a problem simultaneously in both reference frames. See the difference between one and the other and the other reference frame in analysis of a problem. And why don't we actually try to figure out what the moon does or a satellite? It's a relatively simple problem because we have only very simple free body diagram. Because how many forces do I have to identify? How many forces do I have to include on the moon? Obviously, all of them. But don't tell me all of them. Tell me how many. Just one gravitational force, right? So, let's say. So here we have Earth and Moon somewhere there. Let's say that this distance here is r. Distance between the Moon and the Earth. And let's solve it in an inertial reference frame first. So in an inertial reference frame, obviously the reference frame of the Earth, of the surface of the Earth, of this classroom is wrong. It is already sufficiently non-inertial that it won't work. Moon moves too slowly. If if it was rotating, I mean, if it was circling Earth every 10 minutes, then we could consider that it is inertial. However, it takes Moon 1 month, so for that period of time, non-inertiality of our rotation resulting from our rotation is already too significant. However, I can take a reference frame with the origin at the center of the Earth and fix on the stars. Do you understand which reference frame I'm talking about? Yeah, so in this reference frame, we really spin. But forget about the rotation of the Earth. Just consider the center of the Earth and axis now along the stars. So in this reference frame, Moon circles the Earth once a month. And, well, we draw the free body diagram. We recognize that there is only one force exerted on the Moon. It's the gravitational force exerted by the Earth. And because of that force, the Moon is going to accelerate toward the Earth. And, well, I can write down an expression for this acceleration. It moves approximately in a circular orbit. So this centripetal acceleration well, and it doesn't matter actually how we write it down to what quantity we relate it. We can relate it either to magnitude of angular velocity or to speed. How about if we relate it to the speed? So it will be speed with which Moon moves divided squared divided by the divided by the not radius but the distance from the two objects. Actually, I noticed that a lot of you think that since we use letter R, it has to be radius. Radius is only for a spherical object or a cylindrical object. They have radii. From one point to another point, it's not a radius, it's a distance. So do not confuse radius with a distance. All right. So Moon accelerates. This is magnitude of Moon's acceleration. We recognize that there is just one force. So the net force is going to be equal to that force, to the gravitational force. How about if I write just its magnitude? So magnitude of the net force is equal to magnitude of that gravitational force, and it is equal to gravitational constant, mass of the Earth, mass of the Moon, divided by square of the distance between the two objects. Well, in an inertial reference frame, Newton's second law is satisfied, which means that this force must be equal mass times this acceleration. So I can write down that gravitational constant, mass of the Earth, mass of the Moon, divided by square of the distance between their centers, must be equal to mass of the Moon times its centripetal acceleration. So that way I find a relationship between mass and mass cancels, and I see that speed of the Moon must be related to the radius, must be equal to square root of gravitational constant, mass of the Earth divided by the distance between the two objects. This is how I would find what is the relationship between the speed with which Moon has to move and the distance between the two objects. In an inertial, well, it's still not exactly inertial, but relatively quite inertial reference frame, This formula is better for lighter object than the moon, because actually it would be even more appropriate to talk about, let's say, a satellite, because well, in the reference frame which we analyze the problem, it is pretty close to inertial reference frame, because Earth is much heavier than the moon. It is much more massive. However, looking at the problem accurately, we see that there is an error resulting from non-inertiality of the reference frame, because what kind of force is exerted on the moon? Oh, sorry, on the Earth by the moon? Gravitational force. Which way? To the right. How the other force compares to that one? How? Smaller. Wrong. Wrong. The same. In magnitude, they are the same. Newton's third law says, I mean, you got into this trap for the second time already. Yeah, because previously I asked you who is pulling whom stronger. Earth, me, or I pull Earth stronger. And they pull each other with the force of the same magnitude. Newton's second law says that the two forces have the same magnitude and are oppositely directed. So the moon pulls Earth with exactly opposite force. Well, which means that, and what else exerts, I mean, in our consideration, what else is involved? What else exerts a force on the Earth? Sun doesn't, no. I mean, it does, but not for this purpose. Yeah, so in this analysis, we can ignore effect of the sun. Well, the moon actually should cause centripetal acceleration of the Earth as well. And in our reference frame, if we choose origin at the center of the Earth, how the Earth is accelerating? It's not, correct? It should, right? So really, Earth should wobble. Yeah, when moon actually moves around the Earth, Earth also should really move around the moon, but in an inertial reference frame, because mass of the Earth is about, well, 80 times greater than mass of the moon, then acceleration of the Earth should be 80 times smaller than acceleration of the moon. It's the same thing if I jump. If I jumped, really, the Earth moves downward as well in an inertial reference frame, but it is so small displacement that I can say that it didn't move at all. All right, but this was a digression. For the satellite, which is even lighter, it is better. And actually, if I wanted to put a satellite on an orbit just above the atmosphere, I would just put here the radius of the Earth together with the atmosphere, gravitational constant and mass of the Earth, and I will get the orbital speed of the spacecraft, which is, for Earth, is about 7.9 kilometers per second. So if you shoot something in this direction at such speed, it is going to circle the Earth. All right. This was a solution in an inertial reference frame. Consult actually with each other what forces we included in the analysis and what acceleration we took in the solution. Okay, now when you comprehended this approach, I'll show you how to solve this problem in a non-inertial reference frame. Well, so this time I will choose a reference frame, again with the same origin at the center of the Earth, but I'll put the moon along x-axis. So now the reference frame rotates together with the moon. Let's find out what is acceleration of the moon first in this reference frame. How about if we think about location of the moon in this reference frame? Where is the moon? Where? No, Earth is at the origin. Earth is at the origin. Where is the moon in this rotating reference frame? What do you say? 0. Why 0?
You're assigning x-axis to the location.
All right, so x component is r, not 0. X component is r all the time, right? Y component is 0, and z component is 0. Correct. Yes, the position of the moon is in this reference frame is going to be r, 0, 0. These are the three scalar components of the location of the moon. All right. Let's find velocity of the moon in this reference frame. Velocity is a 0 vector, correct. With y and z we have no problem, right? Because we have to differentiate 0 function and 0 function. So it's a 0 function. Now, x stays constant. X is equal to the distance between Earth on the moon. Orientation doesn't matter now. It's on the x-axis all the time. So x component of position is constant. Therefore, when I differentiate it, we will get 0. So in this reference frame, in the reference frame which we picked, the moon does not move. It stays at a particular location. Do you see that? All right. So velocity is 0. Find acceleration. 0. Correct. So we got that acceleration in this reference frame is 0. Well, obviously, Newton's second law is violated over there. See that? Because we don't have more interactions. It's only gravitational interaction. So we have still the same net force. Net force has still the same value, and acceleration is 0. How come? Well, if we want to analyze the problem in a non-inertial reference frame, I have to include now fictitious forces, right? What fictitious forces can we identify over there? Well, let's say Coriolis. Now, Coriolis force depends on this, how fast the reference rotates in an inertial reference frame, which means that we will now we will have to see how fast the x-axis rotates. How fast does it rotate? How many rotations does it make, or how much time does it take to make one rotation? How much? 24 hours. No. A month. Correct. A month. It has x-axis follows the moon, right? So really the angular velocity or magnitude of angular velocity is angle. It takes angle of 2 pi over 1 month. All right. Now Coriolis force requires that we multiply this the angular velocity by what? By mass and velocity. Which velocity? Of the moon, correct. Now I will ask you a difficult question. Which velocity of the moon? Which one? No, it's just regular velocity. But which regular velocity do I have to consider? Well, which one? In this non-inertial reference frame, in that reference frame which rotates together with the moon. We have already determined what is that velocity. It was a 0 vector, correct. So if I calculate Coriolis force, what am I going to get? 0. Which means that Coriolis force is not exerted on the moon. Look for another one. What one? Centrifugal. Okay, let's take a look at centrifugal force. And indeed, we are going to have a centrifugal force. Now let's consider this vector is in which direction? It's in this direction, right? Now let's say that moon turns this way, which it really does. Yeah, moon is traveling that way. So angular velocity is up. If I multiply angular velocity and the radius and that position vector, I will get a vector which way? No, this vector multiplied by this vector using right-hand rule. First, I align my hand with the first vector, and then I have to rotate it in such a way that I can bend the fingers in the direction of the second vector, which means that product is going to be in. So this product is going to be that way. Now I have to multiply, again, angular velocity by this vector. I will get a vector in this direction, and then multiply by minus m. So I will get centrifugal force in this direction. Now, why don't we find magnitude of this force? Which means that I have to take, well, absolute value of minus m, so it's going to be m. Now, magnitude of this vector, I will write this omega, and it's that value, multiplied by magnitude of this vector, times sine of the angle between these two vectors. This is r. And now, what is in our coordinate system? What is the angle between this vector and this vector? Yeah, let's go again. Yeah, so omega and r gives me a vector in this direction. This vector is going to be perpendicular to angular velocity and to that position vector. Now I need to find out what is the angle between this vector and angular velocity. And I have already told you. 90 degrees. Yeah, because product is perpendicular to both. Well, if it is perpendicular to both, it's perpendicular to omega. And now I'm asking you what is the angle of this vector with omega. So it is 90 degrees. All right, now let's calculate magnitude of this vector. So it is m omega, and now I have to take magnitude of this vector times magnitude of this vector. So we squared times r. Now times sine of the angle between them and sine of 90 degrees. Now, what is the angle between, between vector omega and x-axis? Also 90 degrees, right? So here I have another 90 degrees, which means that it's m omega squared times r. Now, from the relationship between angular velocity and velocity, I can also write down that this is speed squared divided by square of the radius of the orbit times r. So magnitude of the centripetal force happens to be mass of the moon oh, what did I do? Oh, this is I wrote that this is the speed with which, because omega is the rate at which the reference frame rotates in a in the inertial reference frame. This is in the inertial reference frame. Now, how fast that axis rotates in the inertial reference frame? It is this. How it is related to velocity, to speed of what? How fast do we change this x-axis over here? The orientation of this axis in an inertial reference frame. Right, with that rate, right? Now, why is it that rate? Because it is supposed to follow the moon. The moon, right? It follows the moon, which means that this magnitude of angular velocity is related to this, how fast the moon moves in the inertial reference frame. So here, this v is speed of the moon in the inertial reference frame. What is its speed in the non-inertial reference frame? 0, correct. Now, in the inertial reference frame, it was that v, right? Okay. So, yes, Taylor.
So by inertial reference frame, do you mean just like any place besides Earth? Or
No, actually, it involves Earth. We picked the inertial reference frame with the origin at the center of the Earth and axis fixed on the stars. So the stars don't move in the inertial reference frame. In this reference frame, in this inertial reference frame, moon circles the Earth. The non-inertial reference frame has x-axis pointing toward the moon. So that non-inertial reference frame rotates in the reference frame of the universe exactly at the same rate as moon orbits us. Do you understand that? Do you understand this, Taylor? Okay. Think about it. I know that, because I mean, what it is that we are so stuck with one way of thinking that it is difficult for us to jump from one reference frame to another reference frame. Oh, you disagree with that?
No, I agree.
Oh, you agree? Okay. Great. So we determined here an expression. We found here an expression for what? What did I calculate here so that we remember what I calculated here? Magnitude of the centrifugal force, fictitious force, right? I found that magnitude of the centrifugal force is equal to mass of the moon, its square of its speed in the inertial reference frame, and the distance between the Earth and the moon. Now, what do I have to do with this centrifugal force? We introduce centrifugal force to save Newton's second law in non-inertial reference frame, right? Which means that now I have to treat it like a add to the forces exerted on the moon, right? So mass of the moon times its acceleration in a non-inertial reference frame, which we found out that is 0, which is 0, is supposed to be equal to the net force plus sum of fictitious forces. Net force is the gravitational force, so it is gravitational constant, mass of the Earth, mass of the moon, divided by square of the distance. Now, let's say that I consider x component. So let's say that this is for x component. So that's 0. Now, gravitational force is to the left, so x component is opposite to the magnitude. And now centrifugal force is going to be to the right, so it is going to be equal to the magnitude. And, well, what is now the relationship between speed and the radius? So I have to solve this equation. I move this expression to the right-hand side, divide by m, and, well, eventually take square root of 2, and I will get this is the speed with a relationship between the speed and the radius of the orbit. Should we be happy with that or not? Yes. Why? See, it does not matter if we solve it in inertial reference frame or non-inertial reference frame. We came to the same conclusion. Now over here I had only forces in Newton's second law. Here I had to include forces and pseudo forces, fictitious forces, to save Newton's, which saves Newton's second law in the non-inertial reference frame. All right, now this equation actually tells us what is the required speed in order to be on an orbit, on a particular orbit. So, for example, if you have a spacecraft, if there is a spacecraft, I mean, I'm going already further. I'm done with this problem. Now I make some conclusions about it. I want to give you a puzzle. How to change the orbit of a spacecraft. And so, let me erase that. Because actually, now, both solutions over here made an assumption that the moon moves in a circular object, or a spacecraft moves on a circular object. This is not necessarily the case. Halley's comet, for example, orbits the sun on a very along a very extended elliptical path. It travels like that. Actually, orbits usually are elliptical, not circular. You can remember that one of the arguments why we degraded Pluto to be a non-planet is that it also has a very elliptical orbit. Sometimes it gets further away from the sun than Neptune. Sometimes it is closer. So it crosses. I mean, it has also very elliptical. We also move along elliptical, not circular orbit along the sun. So most of the time, it is elliptical. However, when we shoot a spacecraft, we don't actually want to have a spacecraft which, well, hits atmosphere or comes to the clouds and then travels close to the moon and back. We want actually to put satellites in orbits which are pretty close to the to circular in shape. And, well, it requires that sometimes an adjustment, changing the orbit. So let's say that the spacecraft moves along the Earth like that, which wouldn't be actually the case because it would, for us, it would cost much more to put it in such orbit than that one, because we are already spinning in this direction. So the spacecraft already on the Earth has certain component of velocity in this direction. But let's say that we wanted to have it that way. How would we change the orbit now to make it still circular? We will have speed, not velocity. Yeah, remember, we cannot increase velocity. We can only increase speed. We will have to increase speed. Now, how to do that? How should we fire? Let's say that the spacecraft travels this way. How should we fire the rocket engines in order to speed it up? Let's say that it is here. Which way? Correct. Yes, so we will have to push it this way. Yes, so we will have to fire the engines backwards. Let me mark it that it is backwards. All right. Well, what it would do, it would put the spacecraft on an orbit like this. should be symmetrical. How to put it on circular orbit? Yes? Fire again. When? Fire it here. Yeah, fire it here again to make it to move with speed which corresponds to this this distance. So we can we would know now this distance over here. We would have to fire the engines in such a way that this speed will get to the appropriate speed corresponding to this radius, and then indeed the spacecraft would start to move along a circular object. Isn't rocket science simple? All right, this will be all for today. See you tomorrow.